Cool. I think we can get started. So there are 10 folks. So maybe we'll just start by asking uh, who all have used any of the distributed databases. Cool. So yeah, okay. So at least a few folks have some exposure to distributed databases. Even if you don't have, that's fine because one of the expectations that I have is maybe after this you get at least some visibility into what happens in distributed databases um, and then it will be easier for you to understand some stuff. But feel free to ask me questions um, in between so that we more keep it more conversational than one way. Anyway, on over Zoom, it's in my experience becomes very tricky. By the way, I just paste the GitHub URL for today's discussions in the chat. So while in the first hour or so, I go through some of the slide deck. Just make sure you clone this repo. This is a Java repo, so we'll be using Java and JDK21 is the version with which this code is compiled. So you will need JDK21, I guess. Even with 17, I think should, but I haven't tried. Cool. So let's get started. I'll just share my screen with okay. So can you see my screen with IntelliJ IDEA workspace? Okay. I can talk in between as well. Don't just uh, cool. So this workspace, as you can see, it has 6 modules. We'll primarily be focusing on first 4, which essentially talk through how we store data, uh, how we store versions of data for what is called as multi-version concurrency control, uh, and then talk through how we implement something called as snapshot isolation in databases. Um, and then there are certain corner cases which simple snapshot isolation doesn't handle. So sections 5 and 6 are mostly that. You can see that each module has exercise.md, which essentially just details out very small exercises that we'll be doing. So these exercises are essentially uh, just completing some incomplete code. So here, for example, you can see that there is this hybrid clock implementation. And what we need to do as an exercise is just complete this now method. So each of these modules have exercises like this. Okay. Yeah, I hope everyone can see the slides now.
Yes, we can see.
Okay. Yeah, I mean, do speak in between because otherwise it's a little hard for me to. Cool. So we'll be talking about, as I said, distributed transactions, and particularly when we say distributed transactions in distributed databases, a lot of tricky things start to appear, particularly in terms of consistency. And we'll talk about what that consistency. I mean, when we say consistency, what that means. And also time, because as we'll see, implementing transactions in distributed fashion, um, using timestamps becomes an important concern. And then the time matters a lot more when it comes to distributed transactions. But first, we'll just very go through some of the basics what do we mean by distributed databases? I mean, just so that we are on the same page. And as you can see on the slide, very simplistically, you can imagine that when we say something is distributed, it essentially runs on multiple processes spanning across multiple machines, right? I mean, that's the basic. Um, and that means obviously databases like Postgres and Oracle and MySQL, they don't fit into uh, uh, this definition because they are not distributed by design. But databases like TiDB, Cassandra, YugaByteDB, CockroachDB, Spanner, Aurora DSQL, they all fit this definition. And to some extent, it's not just limited to databases. So message brokers like Kafka, they also fit this definition. So anything that stores data on multiple nodes and which forms a cluster uh, to which clients interact with, it's called distributed database. Now, when it comes to distribution, and when we are distributing data across database, there are two important concerns. One is that of what is called as partitioning. And why it is needed is essentially simple. You can imagine because we need distribution in the first place because single node is um, cannot handle the load that we have, either in terms of amount of data that we are storing, um, or in terms of number of users we want to serve. And for that, then what we do is essentially we distribute or partition that data across a set of nodes that we have. So this is also called as sharding. Um, and whether you use Kafka or distributed database or anything that's distributed, you will see that partitioning or sharding is one of the important concerns. The other important concern is that of replication. And typically, you will find that any distributed database, from Cassandra to TiDB to Kafka to any other DB, your partitions are never uh, standalone. I mean, you will never have like a single copy of any partition. It is almost always replicated on at least three other nodes. So your replication factor, you will typically find it to be three. In some cases, it can be as low as two, like in case of Kafka. But typically, you will see that partitioning is every partition is replicated on at least three other nodes. Now, in this diagram, we are showing like three nodes. But in practice, another thing to remember is that when we say something as distributed, the designs are such that they can handle, say, few thousand nodes. And that has important implications because obviously Kafka or YugaByteDB or TiDB, they are not designed so that you can run only 3 or 5 nodes, right? I mean, they are designed in a way that allows you to run hundreds of nodes and then have like terabytes and petabytes of data spread across. What we will be focusing on in this is essentially just the partitioning to some extent. We won't consider replication as part of this discussion because you will see that replication and slightly out of context of today's discussion, but replication is typically implemented by consensus algorithm like Raft or Paxos. Have people heard of Raft or Paxos?
Yes.
Yes.
Yeah, and let me see if I can see chat in here. Yeah. So have all people heard of Raft or Paxos or only few? I mean, I'm sure people who use TiDB must have heard.
Yes. Even in
Okay, so
Kafka, we have the care of
yeah,
modified
yeah,
host.
right, right. Um, so we won't be talking about replication, as I said, because when we use consensus algorithm, essentially from client's perspective, even if there are like three nodes coordinating to have consensus on state, from client's perspective, that's like a single entity. So for today's discussion, what we'll do is we'll primarily focus on partitioning, and um, we will essentially, when we write code for transactions across partitions, we'll essentially be doing that with only single node. Um, and and that's because whatever we code with single nodes, once we have in consensus across replicas, it will work exactly the same um, when that partition is replicated. So um, just to clarify that, um, yeah, Amit, please go ahead.
So one question I had is like some databases by design are distributed. Some have been like made distributed. Uh, for example, MySQL does support some versions of distributed setup. Uh, does that mean that uh, uh, like you can build something in a single database format, then it can be converted to a distributed database kind of a setup,
No,
or like so?
no, yeah. So no. So whenever you want something as distributed, it has to be designed from first principles. Like I
Okay.
mean, you cannot essentially have a single node something
Okay.
and then build distribution on top of it. Um, and any
I mean,
attempt to do that,
how will we
uh,
set? I mean, for example, let's say for a transaction, we say, hey, these are like asset properties you have to.
right,
So, is there
right.
any like standard rule set that a database can be set as a distributed database if inherently it supports? Because partitioning and sharding and all, even like MySQL also supports. So, how do you segregate it? Like, okay, this is the level
Right,
of
right.
minimum guarantee that it needs, something of
Right,
that
right.
sort.
So one of the key aspects, and maybe I won't be talking about that much because it's not. So I mean today's discussion is more around usage of time and transactions. But one of the key aspects when you say something as distributed is what happens when things fail. And then key aspect of that is how you manage group membership and failure detection, how you make sure that replicas that you have reconcile when failures happen to make sure that clients see consistent state. Partitioning that way is like a very, uh, uh, I mean, it's required, but the challenges happen when you need to reconcile state and provide consistency guarantees in case of failure. And products which only provide sharding without these other aspects taken into consideration, I mean, they can't be called true distributed in a way.
Got it. Yeah, helps. Thank you.
Yeah, because that's like so how you reconcile data when failures happen um, is the I mean, is the most difficult challenge to solve. And essentially, you need consensus algorithm to do that. So any product which essentially doesn't implement consensus uh, has to have some workarounds. Then, I mean, even Cassandra, for that matter, it is distributed uh, but it doesn't provide consistency guarantees. And even it, nowadays, I mean, they have Paxos implementation from the beginning, but now they also have something called as Accord protocol. Um, for something like distributed transactions. So you need to have that built to call something as distributed, not just sharding. Uh,
Got it.
In
Thank you. Yeah.
Cassandra type of systems, they provide transaction support within the same node, right? So they don't provide
so within
transaction across multiple
Yeah, so
nodes.
Cassandra supports or Cassandra-like key-value stores, which are implemented only with the quorum mechanism. Uh, so I mean, there are a range of things in Cassandra. So yeah, but what you said within partition, they support some level of consistency, but across partitions, they won't.
So consistency and transactions are two different aspects, right?
Yeah, right. Yeah, and I should have pointed that out because when I say so consistency term is a bit overloaded. Uh, it it comes. I mean, we use that when we say consistency across multiple replicas, like what is shown on the diagram. Like
Correct, correct.
it's partition one, and there are two replicas. What is the consistency guarantee between these three? And there is also a consistency guarantee um, when there are concurrent reads and writes happening um, across transactions. And that's a transactional consistency. This is replica consistency. So the consistency is overloaded. What we will be talking about is transactional consistency and not replica consistency. Replica consistency goes into the discussions about the consensus essentially. So let's see how transactional consistency uh, looks like and why it is needed. Again, a very boring textbook example I have on the slide. So let's say you have two partitions and two accounts essentially stored on those two partitions because you are partitioning by account ID. Let's say, and very textbook example, you update an account, then you update another account, like transaction, you are deducting from one account and adding to another account. And what you want is all both these actions should uh, happen atomically within like a single atomic operation, a single atomic logical operation from user's perspective. So it should never ever happen that uh, your account one that was stored on partition one, which was on a different node, uh, it gets updated, but other account doesn't get updated. So if you say when you're updating another account, either your messages get lost or nodes crash, and you get an error back. Then that first step that you took, like the partition one that was updated, that also should be rolled back. Um, so this is when you say acid properties, this is the atomicity property of a transaction that's needed. And databases or data stores which do not support transactions essentially do not support this atomic write. So Cassandra, for example, by default doesn't support if you write to one partition and to other partition. There is absolutely no way to make sure that both happen in one logical atomic operation. Now, which products they support these kind of atomic updates? Kafka, if you know, Kafka sometime back, a few years back, essentially they introduced a feature called as exactly once delivery, and essentially for that, what they needed was you consume, commit, offset, and then produce on a different topic partition, and both these actions need to happen in like one atomic operation. So if you consume and you're something fails and you can't produce, that message should not be considered as consumed, um, and vice versa. So this is very similar to the example that we saw, the textbook example of account update. In Kafka, what you commit is offsets and produce messages. There are new SQL databases inspired by Cloud Spanner. So Spanner is a database by Google, and it's a SQL database. Essentially supports very strong consistency guarantees, and it is distributed. It's actually globally distributed. And then there are open source variants of Spanner, causality and YugaByteDB. They essentially support this two-phase commit protocol across partitions and across multiple rows. MongoDB, as you know, supports multi-document distributed transactions. So it does support two-phase commit. TieDB, someone has used it in the group. So TieDB does support two-phase commit. TieDB is in the same bucket as Spanner, Cockroach, YugaByteDB, with a slightly different implementation and consistency guarantees. So what we saw, just saw is just the atomicity part of it. So like two operations happening on two different nodes, writing to two different partitions, happening as like one single atomic logical operation. But there is another important aspect, and that is called as transaction isolation. So this isolation is essentially, even if there are no failures, let's say, and you are writing to different partitions, what atomicity handles it, what happens if something fails, then the whole operation as such fails. But when there are concurrent reads and writes happening while this operation is in process, then what those concurrent reads and writes see, essentially, if are also reading and writing to the same keys that we are writing to in this transaction. It essentially defines what kind of um, isolation guarantees you have, and this is true even on a single node database like Postgres. So Postgres Oracle, you know that they support different transaction isolation levels, and there are many transaction isolation levels, and they can get very confusing to some extent. But what we will be talking about today is something that is called as snapshot isolation. And snapshot isolation is a very popular and prominent implementation pattern in practically all databases, distributed as well as single node. And the reason is that when you need to provide this kind of what is called as isolation, so that means that same data that's written by that's touched by two concurrent requests, it should not get corrupted, or only completed transactions data should be visible to other transactions. And for doing that, you essentially need to hold locks. And whenever you need to hold locks, you can imagine that your overall throughput um, goes down and latencies goes up, because if there are a lot of concurrent transactions touching same data nodes or same keys, only one will proceed and others will won't be able to proceed, right? So this snapshot isolation, why it's popular, is that it allows you to implement transaction isolation without taking any read locks. So your read operations, and you might be aware that in any user-facing application, typically, if you see the read-write ratio of total number of requests, reads constitute almost 80% or more of requests, and only 20% are actually writes that happen in a database. So if you can implement something that doesn't require you to hold locks for your read requests, then obviously it's going to be preferred, and the snapshot isolation essentially allows you to do that. Now, what this diagram is showing is two things. One, you can see that there is this box called KV, and you can consider it to be a key value store, very simplistically a hash map, um, or a database storage where this key value is a table, and we'll see how your table is implemented on top of a basic key value store. But along with that key and value, there is something called as a timestamp, and you can see TS1 and TS2 as stored. Um, and what that is essentially that marks the version for each record. So each record, when it's stored in the database or in the storage, it is marked by a specific version. Um, and you can consider that version as a timestamp, either a logical timestamp like a counter 1, 2, 3, 4, or a real timestamp, which is time of the day, kind of a timestamp. And any update or insert that happens, even for the same key, again and again, it creates a new version in the storage. So you can see that this key K1, when it's written again, when it's updated by client 2, it goes as a new version at timestamp 2. And what it allows you to do is if another client is reading that particular key and um, you say that that client is reading a particular version at a particular timestamp. So this client 1 is reading at timestamp 1. Every read that this client does, it will always happen at timestamp 1. So even if there is a concurrent transaction that's by client 2, which is writing at timestamp 2, it will never conflict with the read transaction of client 1. So this is very simplistically um, how snapshot isolation looks like. But there are other um, characteristics, I mean, to guarantee some of the key isolation properties of transactions. One, as we saw, consistent snapshot. So once you read a database at a particular timestamp, you are guaranteed to get the same reads every time you read, irrespective of whatever concurrent transactions going on. A transaction that writes as part of itself, when it reads a data, it's guaranteed to get the writes that it has done. So this read your own writes is I mean, it looks very simple, but it's actually very tricky. And if you know object stores like Amazon S3, for many years they did not provide this guarantee. So if you write something to S3 bucket and read it back, for many years there was no guarantee that what you wrote is what you will get back. They added that very recent, I mean, in recent years, in last few years. Then there are some other characteristics like first committer wins to make sure that you and we'll see that by the as we progress in this workshop how to implement that first committer wins. And obviously there are lock-free reads, so reads never take any locks. And so it protects against certain anomalies of transaction isolation. And this transaction anomalies is a very interesting topic because what most databases do is, as I said, any isolation implementation needs you to hold locks on records that you're reading or writing. And because it impacts throughput and latency, most databases take some shortcuts. And those shortcuts essentially involve not taking any locks on the reads. And when you don't take any locks, when you don't hold any locks while you are reading the data, a lot of things can go wrong. And essentially, all the transaction isolation levels that databases implement, they essentially give you like uh, a range of implementation um, lever. Like when you give you a lever that you can play with, and but along with that, you also get a lot of issues when you read or write data. And it's if you're interested, you can just search for like transaction anomalies, and um, you'll be surprised how even single node databases like Postgres or Oracle they have these kind of anomalies. But we'll again talk about what that right skew anomaly is and how that why that happens and how that's avoided by this snapshot isolation thing. But what we will be focusing on now is essentially uh, two things, because these two are the basics of any uh, transaction implementation that's doing snapshot isolation. One, we need to decide how we uh, how and what we use as version. So, for example, if we use a simple integer, we need some way for every transaction to increment that integer and then use that integer as a version. But that whatever we choose as version number needs to be um, monotonically increasing. And monotonically increasing means it should never happen that you give version 1, 2, 3, 4, and then again give version 1. Uh, it should always be 1, 2, 3, 4, 5. It should always increase monotonically for things that happen one after the other. Uh, and there are multiple design choices then that you have. Like single node databases is easy, like what happens in Postgres. I mean, you can just have a simple logical counter because it's only the single node that you use. In distributed databases, it's a tricky choice because you can have like thousands of nodes spanning across. There is no easy way to get this single uh, monotonically increasing integer. And so there are some designs like TieDB. What they do is they have a separate service or a separate process, what they call as timestamp oracle. And anytime you start transactions for reading and writing data in TieDB, the first thing that they do is they always go to this timestamp oracle service and get the next available integer. And that makes sure that they will always get this monotonically increasing 1, 2, 3, 4, and such. Um, Google Spanner is very unique in its design because it uses system timestamp. So any computer has an API to give you system timestamp, right? You if you are using Java, you use system.get current millis and you get current date and time. Um, and Google Spanner uses that with some very important modifications. So it doesn't use um, Linux's get time of the day. But it has a unique uh, time API that's provided by something called as TrueTime, what they call as TrueTime, and that allows them to use system timestamp as a version. Now, the advantage of using system timestamp as a version is that you don't depend on any timestamp oracle, which is a separate service and can become a bottleneck, like what happens in TieDB. Um, But there are issues with system timestamp, and what that we'll see now. Um, the issue with system timestamp, one of the biggest and most challenging issues in distributed systems, is that across two nodes, there is absolutely no guarantee that they will have either have same timestamp, or their timestamp will progress in exactly the uh, same steps. So a clock on my laptop right now might be running a bit fast than a clock on your laptop. And in data centers, that's a very common thing. Across two machines, across two servers, you can have clocks um, uh, which are progressing at a different rate. And that creates an issue because then you can't use system timestamp as a version. And to work around that, what we will see that people who can't have something like TrueTime use a pattern called as hybrid logical clocks, which is a combination of system timestamp with a logical timestamp, and then use that timestamp as a version. So when we say we store version 1 of data, version 2 of data, version 3 of data, essentially that version is this hybrid logical timestamp. We'll quickly go through the problem of clock drift or clock skew across nodes, and then we'll see how to counter that by usage of this logical clocks. So clock skew is everyone aware of that there is a clock skew, and there are things like network time protocol services running um, on all the servers typically. And if you don't have that running, if you forget to keep that running on your servers, you can have some serious issues. So are people aware of that, or you are hearing it for the first time?
Other- And
Yeah.
besides time protocols like PTP and some devices.
PTP, yeah, yeah. So let's see what can happen if we read or if we use timestamp as a version. And one of the key advantages we saw that using timestamp as a version is that it's decentralized, right? So you can any process can just pick timestamp from its own clock and see that this is the version number that I assign to my operations. But with that, if there are clock queues, and by the way, even with PTP and NTP, there can be clock skews because essentially NTP and PTP they rely on network uh, to uh, to fix your time on your machine, right? And anything that works over the network can run into issues. I mean, just because let's say your messages get delayed, or let's say just your NTP service crashes on your machine. So let's say there are these three nodes, this amber, blue, and green. They are three servers, and this amber has its clock showing time as 1, and blue has its clock showing time as 2. And then there is this green server where you actually have your data stored, version data. And there are two versions of this title, and version 1 has a value before dawn, and version 2 has a value before dawn, sorry, after dawn. And let's say there are two reads that are happening one after the other. Um, so let's say your Bob reads first, and Bob reads is handled by the server blue. And then the server blue says that, okay, pick up the timestamp that's on my clock as the read version for this read. So it reads at version 2 and it gets a value as after dawn. And then later, let's say this Alice tries to read, but the read goes to server Amber, and it reads a value at then timestamp 1, which is the clock value given by Amber, and then it will get value as before dawn. And this is an issue because let's say if Bob had read earlier and Amber had read later, what this means is that uh, your earlier read, like Bob read a value that is latest, but your later read, which Alice did, actually got some older value. So uh, this will feel like your reads are going back in time if Alice and Bob talk to each other. So this is the issue with if you use hybrid clock, clock as a timestamp. And so in distributed systems, I mean, whenever you need to use some notion of timestamp uh, when you are coordinating or distributing your requests across processes and servers, something that is called as logical clock or Lamport clock is a uh, very foundational implementation pattern. And how Lamport clock works is essentially we'll see it's just a logical counter that it assigns as a timestamp. So it's not really a timestamp; it's just a logical counter. But what it allows you is to track causality, and what causality means is that if some operation has happened before another operation, uh, and that first operation has actually caused that second operation to happen, then you can track that. Then they are guaranteed to have timestamps uh, uh, which are higher. So later operation will always have a higher timestamp, and previous operation will always have lower timestamp. When it comes to data which is stored on the database, this previous and earlier operations are essentially, let's say, write operations or write and read operations. So if two writes happened one after the other, they are guaranteed to have the later write is guaranteed to have higher version. And in distributed consensus protocols like Raft, um, you might have heard of term called term or Paxos's ballot. Um, or in Cassandra, you have something called a generation number, and they are um, essentially implementations of this Lamport clock. Uh, so how this works is each process which is interacting with other processes. In case of data storages, it will be client processes and server processes handling and firing read and write requests. Now, each of these processes essentially store an integer, and this is a global integer, like global in the sense global scoped by that process. So each process will have this integer, and any operation that this process handles. For example, this blue is handling the write request. It will always increment this counter. And it won't just increment the counter, but the other important aspect is that anytime any process sends a message to other process, like in this case, client is sending this write request to blue, it also sends the timestamp value along with it. So this write request sends not just name Alice, but also the clock value as 1. So when this blue server receives the request, it does two things. One, it checks what its local counter for this clock is, and which is 1. In this case, they are the same. But it picks up whatever is the highest, increments it by 1, and then it stores that at its current value. And it also uses that as a version to store the right value. So this name, you can see that is stored at version 2. And this logical counter is also incremented as version 2. And when it sends the response back, because the rule is that any message that is sent across the set of servers, they always carry this clock value. So it will send this value 2 back to this client. And this client will then handle this response and adjust its own clock uh, to whichever is the highest value between 1 and 2. So in this case, it's 2. And then this actually uh, uh, this chain of clock values is traverses with any operation that's triggered by this client now. So you can see the another write that's happening with uh, uh, the server green. This write now has clock value as 2 uh, assigned to it or sent with it. And with the Lamport clock rule, this green will have clock value incremented to 3, and this title is stored at 3. So what this allows you to do is that essentially looking at uh, this key name at 2 on server blue and title at 3 at server green. If title has a higher timestamp than name, you can infer that title was written after name was written without referring to the system timestamp at all. So this is what uh, Lamport clock is, basic Lamport clock. But Lamport clock has one limitation, and that limitation is that you can compare. So in this case, we said that we can compare version of title with version of name, and that's possible only because there was chain of messages that that caused these versions to uh, relate to each other. So this 3 was incremented after 2 because there was chain of messages of this response and this request that caused that title version of 3 to be incremented. Um, but if there is no correlation like this or no chain of events happening across set of processes, then we cannot compare. And we'll come back to this issue a little later. But another important issue with Lamport clock, and even when Lamport clock is a very popular design choice in distributed systems, when it comes to databases and versions, these numbers like 1, 2, 3, 4, they have no correlation. If a user wants to see, let's say, give me a record as of yesterday, there is no way to do that with these Lamport clock versions. And for that, you need a version that has some correlation with the actual date and time. And that's the reason we in practically all databases like MongoDB and YugaByteDB and CockroachDB, what you will see getting used is something called as a hybrid clock. So we take this uh, uh, design of Lamport clock, which allows us to track causality, like two operations happening one after the other are guaranteed to have higher timestamp, but also have some correlation with date and time. And And that's the solution which is called as hybrid logical clocks. Now we'll go to the code. Now this point onwards, we'll mostly be focusing on code than the slides, because obviously slides are a lot boring, as you can imagine. But if you
I have one question. So basically now the important aspect is the timestamp. So we need the
yeah.
timestamp of which day or which time. So that's why we are going with the hybrid
Yes,
approach.
yes, because the import clocks essentially only are integers, right? One, two, three,
Yeah,
four.
yeah.
So from users' perspective, they don't mean anything, and databases typically will like to give you query support, saying that give me values as of this date and time. And this is a very useful thing to have, and that's why we go to this hybrid timestamp, which is a combination of system timestamp um, and this logical integer, and we'll see how that's implemented. Um, so if you go to the code uh, in module one, we have these two classes called hybrid clock and hybrid timestamp. This hybrid timestamp, you can see that has two components. One is wall clock time, and another is a logical integer, which is called as ticks. And the important method to look at is this: how the logical timestamps are compared. You can see that you generally compare them with wall clock time. But if wall clock times are same, then you use ticks to compare them.
But
And
wall
this,
clock time can have a drift, right, between two nodes. So let's say
yes,
some
yes,
can go, the old value can be.
yes. So we'll see how this tick that we have here, right? It kind of helps you with that. So even if you have wall clock times um, going back or having a skew across nodes, you can use these ticks to tie break and make sure that uh, you have higher versions assigned to later operations. Now, we'll see that in a while. And there are also a few tests, as you can see. So the test might help you answer some of the questions. So there are two important aspects. One is obviously how you manage this hybrid time every time. So this is the thing that we will implement as an exercise. So it will just help us think through a little more on how this helps. But there are tests which essentially walk through the similar scenarios that you just asked. Like if there are clocks which are lagging across the nodes, and you send across these messages with those kind of lagging timestamps, um, how is the uh, causal relation maintained? So what we'll do, I think we can take a quick 10-minute tea break, and you can maybe just familiarize yourself with this particular code. And when we come back, what we'll do is we'll see how to implement this assignment and make sure that. So our goal is to pass all these tests. Currently, they are all failing, and they are failing because we haven't implemented this now method. Cool. So we'll be back in like 10 minutes. And what I will try to do is that like every 1 hour or 45 minutes, we take like quick 5-10 minute break. Also gives you time to like just relax a bit. Uh, cool. So we'll be back by like 11:10-ish. Yes, no, thumbs up.
Yes, yes.
Okay. I mean, it's very hard on Zoom, particularly when I'm presenting because I don't see the. Okay, so we'll be back by 11:10. Cool. So let's get started. And we talked about very basic Lamport clock mechanism before we went on a break, and how it helps us track causality, and what means it means operations which relate to each other, and then we can order those operations to reason about which happened before other or after other. Um, and and then we ended at talking about hybrid logical clocks. So hybrid logical clocks essentially implement exactly the same mechanism as Lamport clocks. So two operations which relate to each other, they are guaranteed to have the later operations are guaranteed to have higher timestamps. And how that's done is we'll just see it in a diagram, and then we'll go back to code and see how we can pass that test or all the
One
tests that we have.
one question, Manish, can I
Yeah,
ask?
yeah,
So if we can solve this problem with the hybrid logical clocks, can
yeah.
we skip this Oracle's implementation?
Uh, so
Is
there
it
are,
alternative?
yeah, it is alternative, yes. So if you can implement, if you implement things with hybrid logical clocks, Oracle you don't need. It's alternative. Only thing is that there are, I mean, obviously hybrid logical clock implementation is a bit difficult than Oracle.
Yeah. Oracle
Yeah.
requires additional system, right? Which
It
needs to
requires
be
additional service, yes,
correct.
additional system, which all your nodes. So if you have all 1,000 nodes, they will need to talk. I mean, at least at the start of the transaction, they will need to talk to that Oracle. And if Oracle is down, you won't be able to proceed with any of the transactions. With hybrid logical clock, uh, you get rid of that limitation because essentially each node can just pick up its own local clock value.
Decentralized.
Yeah, it's decentralized. Yes.
Okay.
Yeah. So very similar to Lamport clocks, you can see that any process, so this client process or a server process, they keep an instance of hybrid clock, and that's the instance that you see in the code. If you see in the code the hybrid clock class, you can imagine an instance of that class is kept in each server process. And very similar to Lamport clock, you will every message that's passed across carries that hybrid clock value of the source process. So in this case, client is sending a write request. It will have the hybrid clock value of this client, which is passed. And when the server receives this request, very similar to basic Lamport clock, it needs to now merge the received hybrid timestamp value with its local timestamp value. So what it does is it reads the local clock. In this case, let's say it is 1,000, but because the value 1,000 essentially is a actual timestamp value, so it can be anything when it reads. But it does the comparison with the incoming request. So it will pick up whichever is the highest, and it will increment the logical counter if there is no change. in the timestamp value. So even when you have or it will pick up the largest, I mean, similar to the Lamport clock rule. So even when you have the same um, timestamp values passed along, you can see that this timestamp probably had not incremented or it was lagging. So when the message was received, the value you get for the timestamp is same as what was at the client before the message was sent. But then what you do is you use this counter as a tiebreaker. So you increment that value. And what this guarantees is that if you are assigning or incrementing this timestamp after the message was received, the timestamp value is guaranteed to be greater than the timestamp which was carried through this message. And then you will, whatever operations you do, like in case of read and writes or writes, in this case, you are storing the value. You will store that with that timestamp version. So instead of just storing at name at version 1, you will say name at timestamp 1000, 1, which is the hybrid timestamp value. And very similar to Lamport clock, you will return because timestamp is carried with every message. You return that to the client. The client adjusts its own clock based on the values that are returned. And now the next message that it sends, it will send this adjusted value. And now you can see that the next message goes to this server green, which has its own timestamp progressed to say 1005. So this merge will definitely pick up the latest value, which is 1005, and it won't need to increment to this logical counter. So the writes that it will do, it will be at 1005. And that's how then will progress. So then this 1050 will be passed to client. And even if, let's say, client process's clock was lagging, it will now be updated to this 1050. So I mean, this is how basic hybrid clock operations work. So what we'll do now is see if we can look at the code and pass this test. I mean, first maybe let's just look at the code. So you can see this hybrid clock implementation that we have. I mean, we have it in Java, but which is almost exactly the same as if you can traverse through these URLs for CockroachDB, YugabyteDB, and MongoDB. It's almost exactly the same. It's important to remember that this will have one instance per server process. So each server process will have one instance of hybrid logical clock. So anytime you need to call things like system.current-time millis, you will instead call hybrid clock instance.now. So anytime you need to use timestamp, you will always use hybrid clock instance.now. Now this hybrid clock itself, it has two components, as you can see. One is that of a clock, and this clock is essentially just an interface that we have so that we can stub it in our test. And there are two implementations of this you can see. One is the system clock, and the system clock is just giving you system.current millis, the actual date and time. And then there is a stub clock, which essentially you can use in your tests so that you can control assertion on specific times. The other important aspect is it always tracks what was the latest time so that it knows whenever you call clock.now, that means system.current millis, you can see in case time goes back because of NTP adjustments or other things, you still pick um, the later timestamp. And there are two important methods. One that is this now, which you will always call whenever you need to assign a timestamp for anything that originates on this process. And then there is a tick method, which accepts um another hybrid timestamp. And this tick essentially what it's doing is merging the timestamp. So this is where so that Lamport clock rule that we talked about. That's what this is where it's applied. So it picks up the latest of the current wall clock time or the request time or the latest time, the latest time that it tracked. And you can go through this code, which is a bit involved, but essentially what it's doing is if your wall clock time has not changed from the previous time, or the request clock time and your wall clock time is the same, then you essentially do a tie break by incrementing the ticks. And then there are some very basic tests. The first test, what you can see happening is we are using stub clock. So that means instead of system.current millis, it will always return value 1000. And what we are expecting is if that system.current millis gives you the same value, then your ticks should go on incrementing. Whenever you say now, and your system time is not changed, then your ticks should go up. And the other two requests are essentially about merging the timestamps. So you have hybrid clock with a particular timestamp and you received another timestamp in the request. What is the merge timestamp that you can use? And in this case, it needs to be the higher of these two, plus because it has ticks 5, then you need to increment the tick by 1. And the next request is essentially when you receive a request with a very low system timestamp and your own clock is ahead, then you need to pick the latest one. So you can take like 5 or 10 minutes and try to implement this now method and see if test passes. Is that fine? And we'll,
Yeah,
we'll
sure.
in 5 minutes we'll look at the solution. Oh, okay. So let's see the implementation. I mean, what can make all the tests pass. Um, oh, it's not shared. Okay, let me just share. Cool. So if you can just do something like this, you call the tick method with the latest time that you're tracking. It essentially give you the next time because tick also always checks the current time and then it merges that with the latest time. So if the latest time, uh, I mean, in case your clock goes back in time or there is no change in time, it will all be handled if you just do this. Cool. Yeah. And you can go through, I mean, maybe later these URLs, I mean, just to see how it's actually implemented in production, which is very close to what we have. Um, but other important aspect is that using this hybrid timestamp, essentially what you use it for is storing your data and assigning these hybrid timestamp values as versions to your data. So the next important aspect is how to use this hybrid timestamp to actually store data in a key value store. Um, so the next two modules, modules 2 and 3, essentially we have code which demonstrates how version data is stored in databases. And the code that we will refer to is very close to what actually happens in production. So if you look at TiDB or CockroachDB, YugaByteDB, MongoDB databases, you will find something similar. So there are two things that are important, and if you look at this diagram that's on the slide, it's showing there are three versions of uh, a key account one that are stored in a key value store. So account one at 1110, account one at 90, and account one at 50. Uh, when you read a particular key, like in this case, account one at particular version stamp, uh, like in this case, read timestamp is 10 or read version is 100. Sorry. Then the important requirement that we have is there might not be uh, a version which is exactly matching the version number or the timestamp number at which we are reading, right? So in this case, you can see that there is a version at 90 and at 50 and at 1110, but what we are reading at is 100. And for doing for actually what's expected in this case then is that whenever we read at a particular timestamp value, what the storage should return you is if it's an exact match, then obviously you get the same version. But if it's not an exact match, then any version that has the highest timestamp value or the highest version value, which is lower than that 100. So in this case, what it should return you is account at 90 because that's the highest version that's available at timestamp 100. So you should get back 150. Uh, so you need whatever storage you use, it needs to provide you this kind of a mechanism. The other important aspect is a lot of times we need to read all the versions starting at a particular version. So you give me all the history starting at version 100, and for that we need to go back and um, get all the versions like at 90 and at 50. And to achieve these mechanisms, uh, we need all the data in the storage stored in a sorted order. So you need all the versions stored in a sorted order together. It should not happen that like if you use like a simple hash map, for example, you can have all your versions scattered around. So there is no way to quickly go to a particular version and then traverse back in time. Or there is no way to implement this kind of a use case where if there is no exact match, you give uh, the highest number lower than what the read timestamp is. So you need this version stored in a sorted order. That's the key requirement. And for this, you will see that the most common data structures that are used are in production, which you will see skip list as a data structure that is used. It's a very common data structure. Um, have you heard of skip list? Any of you?
No.
Okay, so we won't directly use skip list, but it fulfills all these requirements that it keeps all the keys. So it's a key value store or like a map kind of a data structure, but it keeps all the keys in sorted order, and it's very convenient because it fulfills all the use cases for version storage. What we just looked.
It's something like a memory sorted,
So
sorted order.
I mean sort linked list. You can very simplistically. Yeah, I mean it's a linked list, but a little more, and that's why it is called a skip list. So what and skip list is something. I mean, it's kind of a you can consider as a logical model for what storage is like RocksDB. Have you heard of RocksDB as a storage?
Yes.
Yeah.
Yes.
So RocksDB's API, if you see, is almost exactly the same as what a typical skip list API gives you. And you will see that RocksDB is almost universally uh, used as a storage engine for practically all databases, like all its CockroachDB, YugaByteDB, um, or
TiDB
even
also uses. TiDB also uses that.
TiDB also uses RocksDB. Nowadays, a lot of these databases move to their own implementation, uh, which is API compatible with RocksDB, but have their own versions or own modifications done to that RocksDB. So RocksDB is a very good storage engine to be aware of. I mean, just to know how storage actually happens in databases on when you store on disks, and how it differs from something like Postgres, for example, which uses or something like Mongo in some cases where they use persistent data structures like B plus trees. So what we will do is, if you look at, is my screen shared? Yeah, I think so. So if you look at this module 2, uh, this module 2 has a few implementations of what is called as this MVCC store. So MVCC store is just a logical interface which is typically supported by all the version storages like RocksDB. And what we will look at is an in-memory version of this MVCC storage, and then a persistent version of this MVCC storage. In-memory version you can see is it uses a skip list uh, from Java standard library, and the persistent version will use RocksDB. So, I mean, in the interest of time, we obviously won't be implementing the whole thing, but this is a good reference code to have, and we'll just do a small implementation tweak to make all the tests pass. So there are tests around all these implementations.
So, this all the versions for every key will be maintained or stored in the storage, right? Or
Yeah,
after
yeah.
certain time it will be deleted or something. The old
So
versions.
obviously, when you have version storage, there is some kind of garbage collection that happens. Garbage collection in the sense, if you keep on accumulating your versions, uh, after some time, your older versions will be deleted.
Okay. So that will be
But
configurable
yeah,
in,
but
in
will
config.
that will be configurable? Yeah, yeah, yeah. So we will look at how this version storage now works with hybrid timestamp as the version. Uh, MVCC key. So any data that we store, and we can model any data storage as a key value storage. I mean, starting from your uh, Kafka-like message brokers to write-ahead logs to actual SQL databases. Any data that you store uh, will have a key and then a value. And this key has two components. One is the actual key that you are trying to store, and the other is the hybrid timestamp, which we just looked at. Important
One,
implementation aspect. Yeah, sorry, go ahead.
one question. So now these databases are relational multimodal. Some are like multimodal, right? Like for example,
Yes.
Spanner, they say like we support all type of things.
Yeah. Yeah. Yeah.
So every data, the model, it will be stored as a key value.
Key
Every
value.
column
Yeah.
will be
Yeah. Yeah.
stored as a key value. Is it?
Yes. Yes. I mean, we'll if you see in that module, that version KV, there is a class called as table. So what we'll see is just an example of how a row in a relational model is stored. So how you model a table on top of a key value store, which is
Okay.
this MVCC store. We'll look at that in some time. Yeah,
Okay.
yeah. But any data. So when you say something is a multimodal, essentially any data you can model it as key value and then store it as key value. What you call a key and what you call a value is different. So in a row-oriented database, your value can be entire row. In a column-oriented database, your uh, or columnar databases, your value can be um,
Only one column.
only one column or a group of columns.
Oh.
Uh, and
Like they
in a
call it
document,
as a projections in
yeah,
analytical
yeah,
databases.
yeah, yeah. And in your document database, your key can be just a document. Sorry, the value can be just a document for a given key.
So wherever the filter
Yeah.
conditions are applied, then that will be stored as a separate key
Uh,
value.
which filters?
Like for example, in MongoDB, we query based on some filters like conditions, right?
Yeah, but that will be your query processing uh, part. I mean, not necessarily how you store that data. But if you have indexes, then they will be stored.
Indexes.
yeah, so indexes will be stored independent of this. So this is your raw data.
Hmm.
And pattern indexes will be stored in either in a separate. But for this MVCC key, because we saw for storing version data, it has to be sorted. It's important to implement this comparable. So anytime you um, uh, represent a versioned key, uh, it's important to have a way to compare those keys. So what we'll do is we will compare, we'll implement this compare to method, and then there is a corresponding MVCC test that we have to make pass. So take some time just to go through this code. Now, one of the key and very important aspect is that you see that this key is a byte array, right? So it's not a string or anything else. It's a byte array. Um, and what this allows is essentially you can have any data type stored as a key, representing that as a byte array. But it also has an important implication that whenever you convert your key, like in our tests, we have string keys, but let's say you have other composite keys which are encoded into byte array. That byte representation of that key needs to be comparable. So you cannot just randomly encode a key into a byte array. Um, when you have two keys with the byte array representation, let's say 1 and 2 as numbers, and 1 and 2 you encode as byte arrays. If logically that 1 is less than 2, then whenever you compare these byte arrays, uh, it also should compare as if byte array representation of 1 is less than byte array representation of 2. And just to simplify, I have this code commented in here. You can just uncomment and make things pass, but do go through it and make sure you understand what's happening. But why you need that key to be byte array is that when you actually store it on the disk, either in a file or in the RocksDB, essentially when it goes on the disk, there is no data type associated with it, right? So data,
Serializing.
right? So you need to serialize and then store. And then at storage engine level, any sorting happens. It essentially happens on a byte array comparison, byte by byte comparison of any encoded data that you store. Cool. So maybe take 5 minutes to go through this code and make sure all the tests pass. If you just implement this compare to, all the tests will pass. And one thing you can try to answer or try to figure out is we are doing this compare unsigned and not just arrays.compare. Cool. So all the tests passing for everyone. And what we'll do is we'll just go through that implementation and discuss if you have questions. So, share my screen. So let's just go through the in-memory MVCC store test. And this in-memory MVCC store is using concurrent skip list map, which is a JDK library implementation, and uses MVCC key as the key and um, any value as a value. Now, if you look at the implementation, I mean, put is very simple. Put is just one put. We'll come to put batch in a while. But the get methods are interesting because in get, what we need to do is there is always a possibility that you won't get exact version, right? Like in the PPT we saw that you have versions up to 90 and you are reading as of 100. What you should get back is 90, and it should not be that you don't get any result. So this concurrent skip list map, even if you have like sorted linked list, it will have an API to get like a floor entry for a given key. So it will give you the highest entry lower than this key. You can always get the latest by trying to give the highest version. So if you just give it the version as like with long and integer max values, you will get the latest version for any particular key. And then you have a method for traversing the history. So you get all the versions up to a particular version, which is implemented by using a submap. And we'll look at scan prefix of in a while. If you look at the tests, this is how we are storing. So we are storing account balances. So let's say this account ID, account 1, and we are storing balance as a value. Now you can imagine it to be a document database where account and account details is account detail JSON currently just has a balance attribute. And while storing that, you can see that a MVCC key is first encoded. This account ID string is encoded, and encoding is done by the encoding or codec implementation, which is called as order preserving codec. And I have put their GitHub URLs for actual production implementation. So whenever your Cockroach or Yugabyte or MongoDB actually store keys in this kind of sorted storages, they need to do this order preserving encoding for keys, so that all these operations that we looked at, right? Floor entry, scan up to, and seek, and other things actually work well with binary comparison of byte arrays. So we encode both keys and values in using that order preserving encoding. Value doesn't need to be order preserving, keys need to be. So this is just the in-memory version. Now there is a RocksDB MVCC store. that you can look at, and this is actually using RocksDB underneath. So you can imagine this to be um, any database like Mongo or TiDB or Yugabyte. Uh, they essentially use RocksDB like this. So RocksDB um, instance you create, and then you have put same methods, right? I mean, all that we saw on the in-memory database, all those methods are implemented on RocksDB because RocksDB is API compatible with a sorted data structure. Now, a crucial
So
thing here,
this just one
yeah,
question. So basically,
yeah,
this
yeah.
MVCC is on top of RocksDB, right? Key value database.
So MVCC, to implement MVCC storage, you need uh, some sorted persistent implementation. And RocksDB is almost like a universally to be to be a storage implementation that you can use, and it fits very well for storing multi-version storage or multiple versions, because it is a if you know of LSM trees, it's a LSM tree implementation which
Correct.
is inherently a sorted storage, which fits very well for versioned storages, because the API that you need, something like essentially get as of or get latest or seek or traverse history and stuff like that with version storage. RocksDB works very well with that.
So
So
if I
yes, so
have to visualize how it is
yeah,
going to be stored, basically this version, the key, actual key at the top level, and it
right.
added with the version, and then you will get
Yes,
a unique combination, and that combination becomes the actual key in the RocksDB.
yes, yes, yes. So there are tests. Again, I don't have assignments, but there are tests for this RocksDB implementation as well, and see if they're passing for you. So what we are doing is that we are constructing a MVCC key with uh, with the hybrid timestamp. So this TS is just a utility method for test, which gives you a hybrid timestamp value. So this new key, when we construct for this actual logical key author, it is created with a hybrid timestamp value of 10, and you can actually debug and see this kind of test. If you see this key, it's a composite key, right? MVCC key, as you said. So there is a author part, and then there is a timestamp part in this MVCC key. Now, another important, particularly when we are storing in RocksDB, because RocksDB doesn't understand MVCC key. MVCC key is a Java object that we have. So when we store that in RocksDB, we need to encode this Java object into a plain byte array that RocksDB understands. And this encoding again needs to be order preserving. So when you encode a MVCC key into byte array, that resulting byte array should, if you compare like two MVCC byte arrays constructed by two MVCC keys, they should have exactly the same comparison that this particular compare to gives you, right? Because otherwise it won't work with RocksDB kind of a storage. So what you need is similarly when we just had this logical key of author and others encoded uh, when we stored that byte array in memory storage. When we store in RocksDB, we need to encode this MVCC key itself. And this is like a very simple encoding that we are doing, like just converting this MVCC key into byte array. And this MVCC key, you can see that it has like three parts. First is the logical key that we had. Then there is a hybrid timestamp which has two parts, right? Wall clock and ticks. So essentially, we need to construct a byte array representation of that, and we can just keep the key byte array as is, and then we put uh, hybrid clock components, converting them into byte array essentially. So here we are using the byte buffer implementation of Java, which has some helper methods to put long and ints. When we actually encode them, and we'll look at why that we are doing that. But this is a very important aspect to remember, because your storage doesn't understand Java or other objects, right? So it will only implement based on the byte array comparison. So any questions on this, or you want to take some time to go through particularly the RocksDB implementation?
I think at a higher level understanding, it is clear. Like we have a composite kind of a key,
Yes,
which should
yes,
be sortable, so
yeah,
that the compare we should be able to compare and sort it. So that is
yes.
the primary requirement, and
That is the
remaining
primary.
everything is taken. The storage part is taken care by the evaluate service.
Yes,
That is
yes,
in discussion also.
yes. Now, one important thing, as I said, and that's crucial to understand, is that uh, when we implemented compare to method, right, in MVCC key, uh, we assumed that the versions are um, uh, arranged from lower version to higher version, right? So but when we store it in RocksDB, I mean, one thing that you need to be just
It's
I mean, it's
basically monotonically increasing,
monotonically
uh,
increasing, yes,
and
but when you
encoding should happen.
right. I mean, it's not really essential to know, but just a tricky thing. I mean, if you read Yugabyte DB source code or CockleDB source code, Yeah, so if you look at this encode MVCC key, I mean, I've tried to put a comment there. Just a minute, let me just take this call. Sorry. So if we look at how this hybrid timestamp is encoded, it's actually inverted. Uh, so you will have higher versions stored earlier than lower versions in your sorted data. And that's essentially because we'll be using standard iterator methods, right? So if you see, we use this stick. Just a minute, this is called. Yeah, cool. So one other thing that we talked about is essentially on this basic key value, how we represent something like a table in relational databases. So if you can see this table test, share, it's not shared, right? Okay. So there is a class called table that we have, and it has some utility methods to store rows of a table. And so this is just a demo purpose. We are not implementing anything. Let me see if this test passes. And I think I have, right. So there is this test to demonstrate how you can represent a row in a table. So let's say we have this table called customers, and table, when we say it internally has this MVCC store. It can be a RocksDB store or a, so the test we are using a RocksDB store. And when we are inserting a row in a customer for customer one with columns name, email, and address, it can essentially be modeled like this. So you have a table with insert row where you insert all these key values. So each column has a key, and essentially for row you have a primary key. And this is where you are using a put batch method on this MVC store. Now, put batch, what you need to use is a database or a storage engine like RocksDB. It guarantees that a batch, when you insert a batch in RocksDB, it's inserted atomically in the lower level storage. So you will either have the entire batch stored or none of it. And particularly when you implement a row-like thing, you want entire row to be stored and not just a few columns. So any questions on this particular table row implementation? Or is it clear to everyone? No questions.
Yeah, I think it is clear.
Clear, right? Yeah. So there are few um, design alternatives that you have. So what you can see here is that when a row is inserted in a lower level storage, each column is stored as a separate key. So essentially, what you get into the storage is multiple keys, one per column, getting stored, which then represent one logical row. An alternative could be that we serialize that entire row, like all the columns together, and store them as a blob. So each key will have a blob associated with it. So and that's a design choice that your database can make. There are pros and cons for each design choice, and I think I do have slides for that. Let me just check. Yeah. So if you look at this slides, I mean, what you can store is if you have like this name and status as like a single row. That single row can be um, encoded as a byte array, and you store a key and that entire blob, versus you store each column as a separate key. And why, particularly with version storage, why each column stored as a separate key helps better is that when you update only a few columns, you don't need to um, have like that entire row duplicated again. So in if you create a blob for your entire row, even when a single attribute is updated, you need to actually create a one more copy of that data with each column stored as a separate key. You don't need to do that. So typically you will find databases like Yugabyte DB, which are SQL databases, they choose this option that each column is stored as a separate key in your uh, RocksDB storage. And when you store each column as a separate key, then reading a logical row, um, you need to do some extra work. So if you look at this get row method, you now need to construct a row by scanning through the entire column space, right? So all the key values for all the keys um, for all the columns for a given row, you need to scan and then construct that row. If you store this row as just a single value blob, then you don't need to do this. So this is the extra work that you need to do. And this is where, because we are anyways storing everything as a sorted order, this prefix scan kind of a implementation helps you. These are little more details that you probably don't need for transaction implementation understanding, but some nitty-gritties that if you are reading source code of all these databases, you will come across these aspects. So we'll look at quickly the third module in the source code.
Unmesh, just Jainab asked me to remind you for the lunch
Yeah,
break at 12:45. So,
yeah. In 10 minutes, we'll take a lunch break
yeah.
for an hour. Yeah. So what we looked at up to this module two is that we were looking at first we looked at hybrid timestamp and then how that can be used as a version to store in a particular MVCC store. Now in distributed databases, when you say distributed databases, there are multiple storage nodes that will have, right? And then each of these storage nodes will have its own MVCC store. So this module 3 just demonstrates how a typical distributed storage looks like. So each storage replica having its own MVCC store. Now in partitioned databases, this will be each partition, right? So let's say we have different nodes or different processes, each having its own MVCC store. Each of that process will have its own version of hybrid clock. And then these servers or these processes handle write and read requests. So these are uh, the user requests that are coming to these storage nodes. And then you will have a client which needs to route. So if you have, let's say, these three nodes, uh, a client needs to route a particular key to a particular node. So if let's say we are writing these three key values to the cluster of three nodes, and you look at client.write, you need some logic to route a particular key to a particular node, right? That's what you will need to do. And do you see where this routing is done? It has to be done somewhere, right? So where do you think that needs to be done?
Does the client lies in one of the nodes or is it a separate
So let's say right now it's a
entity?
separate process. It can be in one of the nodes as well, if you think nodes handle the client request. But let's say for simplicity, it's a separate node right now or separate process. But it knows about all the nodes, so it has metadata about all the nodes. That's how it is modeled right now. So whenever you do this write, it needs to route to a particular node. You can see that there is this replica for key method, right? And what it's doing is taking hash of the key and modulo size of the replica endpoint. So currently we have like 3 nodes, right, where we are having storages. So hash of the key modulo that size, and whatever the index we get replica or the node at that index and route that key to that node. So if you have like 3 nodes, we expect each key to go to separate node ideally. I mean, it might happen that two keys go to 2 different nodes. But your cluster will look like this, and your client operations will look like this, that you have a client writing different keys to different nodes, routing them based on a key. And here we are using simple key values, but as we saw in the last table implementation, it can be a row in a table. So your table, what you call a table, is essentially sharded or partitioned across multiple nodes. And based on the key that you are writing or reading from, it will be routed to a particular node or process. What we'll do, so we'll take a lunch break, but when we come back, what we'll do is I will briefly walk you through the framework that we are using. So this framework is called Tickloom, and it allows us to do things like this, that we are creating an in-memory cluster of nodes, each implementing the storage replica um, implementation, essentially. So each node represents a storage replica, and then it allows you to route or have clients sending requests to these servers. And it has some additional facilities as well, this particular Tickloom framework, which allows you to simulate error conditions. So if you want to like enable network delays or network faults, currently we won't do any of that. But coming back to the point of transactions, um, if we have a basic clustered implementation like this, that we have 3 nodes and clients writing to all 3 nodes, random keys and values, the next thing we need to do is have this storage replica implementation in such a way that whatever we store in this MVCC store needs to be atomically stored across replicas. So across this storage node 1 and storage node 2 and storage node 3, whatever we store needs to be stored atomically. So what we'll do is we'll take a lunch break, and when we are back, we'll see what this Tickloom framework is, and then also look at this module 4, which is essentially on top of this basic clustered implementation. We will implement transactions. We'll implement essentially transactions using snapshot isolation. Cool. So we'll be back by what, 1:30 or 1:45?
145.
1:45. Okay. Yeah. Okay. Cool. So we'll be back by 1:45 then. And then that's the Mm, okay. So let's get started. Let people join in. So before we went on a break, we looked at essentially version storage and how hybrid timestamp is used as version for storing in storage engines like RocksDB. And just before we went on a break, we also looked at how partitioning client can route requests based on keys to different replicas. And now what we'll do essentially is the crux of today's discussion is we'll see how snapshot isolation is implemented now, previous modules, and hybrid timestamps. So let me just share my screen. So we'll look at module 04, distributed transactional KV. And the key implementation is in two classes, essentially transactional storage replica. So this is essentially the server side of things. So each node essentially runs this particular object in its main method, which has its own MVCC store, and we'll look at why there are two separate stores. And it handles these kind of requests. Now, again, just to recap, we are using a framework called Tickloom. And I think I just have a very simple hello world for this Tickloom, just to demonstrate how you can implement client-server communication and clustered implementation in your tests. So your server side needs to implement this kind of a replica, which extends the base replica object. And then it needs to register the type of requests it handles. It can be either client requests or requests that happen peer-to-peer. Each request is handed over a message, which is essentially an encoded request. So the server needs to decode it, the request that it expects, and then it can send the response back. This base replica has all the facilities for sending messages to different replicas. It has access to the network implementation, the storage implementation to store data, as well as sending messages across replicas. And what you only need to implement is the type of request and responses that you support, and then a client, um, which essentially routes requests to the server. So, and then you can write your cluster test, like what's shown in this particular test. So you can create a cluster with a set of process IDs, and then you can pass it a factory method for the implementation of your clustered node. Now this, if you are aware of Cassandra or Akka or Kafka's clustered test suite, which essentially builds an in-memory or embedded cluster, um, to then allow them to run essentially integration tests within a single process, and then simulate various failure scenarios. This is almost exactly that, but this implements a technique called as deterministic simulation testing, and we won't go into the details of that, but um, that's what this essentially framework is. And then what that allows us to do is essentially set up a cluster like what we saw in the last this last module, this distrib, something like this. So we created like a cluster of 3 storage nodes. You can essentially create a cluster of 100 storage nodes as well. It doesn't matter. It uses simulated network. It can use actual network as well. But obviously within a single process, it can very well use simulated network, and then really can simulate a cluster of say tens of nodes. So in this transactional key value store now, if you just compare the number of classes and messages that you have, like this is your standard uh, key value store, which can be distributed, and you can see that there are n number of additional messages that you have that replicas need to support, and then there are a lot of other supporting classes as well. So we'll see what that is, but the key classes to look at is transactional storage replica and transactional storage client. And then we'll look at the tests. Essentially, we'll start with the core flow, transactional storage replica core flow. But first, let's try to understand what's happening in here. So when we say we want to implement distributed transactions, essentially there are multiple participants, as we expect, multiple partitions, multiple nodes, and which need to store data atomically. So to coordinate, you need someone to coordinate all those writes that are happening across a set of nodes, and they need to be tracked as a single atomic unit, which is essentially called as a transaction. So we'll just walk through a basic workflow of how transaction works, and you will see exactly this thing in the code as well. But you obviously need someone acting as a coordinator which tracks the status of this logical operation as a whole. And then client needs to tell this coordinator that I'm beginning a transaction, then do a set of actions, and then tell the coordinator that I'm committing the transaction. This is the basic flow. So what this diagram shows is how these 2 roles coordinate, and the storage replicas that we had, they can assume both the roles. I mean, one of them will act as a coordinator, and the same one can act as a participant. So there is no dedicated coordinator process that's running anywhere. It's just one of the server processes that are running. Um, so client tells the coordinator that the transaction it's beginning a transaction, and it assigns a unique ID because each logical transaction needs to be assigned a unique ID so that you know which transaction you are part of. Generally, it is just a UUID that's assigned to transactions, as we'll see. But for the convenience of demonstration, yeah, let's say the transaction ID is one. And then what this coordinator does is it creates a transaction record, just stores a record somewhere saying this is the transaction that's created and the status is pending. And then your client does actual operations uh, with the participants, so writing keys and values. Now, what you see here is the write is called as writing an intent to write. So it's not actually writing to the storage from where data is read. It's storing it somewhere else. And it just stores it somewhere else, and once it's successful, returns a response to the user. Now, this is an important step. So because we want atomic commit in the sense that the data is not uh, essentially available for read unless we know that transaction is committed. If you want something like that, then we need a way to kind of differentiate the data that's written as part of an ongoing transaction versus data that's written as part of the committed transaction. And you will see that in databases like UGabyteDB or CockroachDB or any other databases which use RocksDB as a storage. Uh, you can essentially very easily store in-process writes separately. Uh, in our implementation, we are actually using a completely independent store called as intent store. It's called the same in Yugabyte as well. So all the in-process writes are written to that store, and there is a separate store for committed data called committed store. And any reads that happen, they will by default go and read from that committed store. So this is the first key requirement. Any implementation that needs to support transaction needs to somehow differentiate between ongoing data that is part of ongoing transaction and data that's part of committed transaction. Now, it's important to know that at some point you need to move that data from this place where you're storing ongoing transactions to the committed transaction. And this happens when essentially you commit the transaction. So when you commit the transaction, I'm not showing the commit message going from client to coordinator, but a client is expected to send a commit message to coordinator, and then coordinator can say that okay, each participant, you now resolve this transaction, saying you move this data from um, a separate place where you were bookkeeping it to the committed store. There is one more important aspect of it. So let's say you a client sends a commit to the coordinator, and coordinator sends this resolve transactions to transaction replicas. There are two issues with that. And two issues being, what if the coordinator marks the transaction as committed, and then this resolve transaction request to individual participants, they fail or they never reach the participants. Um, then you have these participants actually in an unknown state forever, right? Because they won't know um, what to do. And this is the reason you might have read that two-phase commit is by default, by nature, a blocking protocol. So if your coordinator fails, there is no way for any of the participants to know what is the outcome of the transaction. And to work around that, um, you will typically how it's implemented in these modern databases is that uh, it's not coordinator's responsibility alone to tell participants that the transaction is committed. Coordinator state, where we are storing the transaction status, that's the final source of truth. But participants also know um, which node is acting as a coordinator, because you choose coordinator based on the transaction ID and the intent records that you store on participants. If it can track that transaction ID, it knows which node can be connected to for knowing the transaction status. And so these messages from coordinator to participant, they can very well be uh, optional. I mean, so if they reach participant, well and good. If they don't, participants are anyway going to connect with coordinator if they don't know what happened to a particular transaction. And we'll see in a little more details what happens. But it also allows you to implement a little faster commit protocol, because you begin, then you write, and then you commit the transaction. You say the transaction status has committed on coordinator, and immediately the coordinator can return to the client saying, okay, it's committed, even before it actually goes and tells participants that the data is actually committed, and that it can do in the background in the asynchronous way. And this actually avoids multiple round trips before the client knows that the transaction is committed. Now, why this is possible, as I said, is that if, let's say, there is a request from client, a read request that goes to a participant, and participant uh, figures out that there is an on transaction for this key that it doesn't know the status of. What it can do is it can go to the coordinator and check what is the transaction status. And if it gets the transaction status as committed, before this read is handled, it can move that data, intermediate data, to the committed state, and then return the read request. So this is very similar to if you know of this concept of read repair in databases like Cassandra. When you read, if there are some nodes which are missing the value, the read repair is triggered before the response is returned to the user. So it's very similar to that. So let's see in the code how this works, and we will try to do some assignments. Actually, just completing some of the code to make sure we understand what's happening. So what we'll try to do is try to make this particular test pass. So if you see, all the tests in this transactional storage replica core flow are failing. So let's try to make them pass. And if you can go to the exercise.md, um, there are a bunch of exercises that we need to make sure we we complete. So the first one is essentially handling the begin transaction request. And if you go to this transactional storage replica, you need to go and figure out where the begin transaction request is handled. And then we need to complete this. So what I will do now is maybe we'll take say half an hour. You can go through all those exercises, and while doing that also familiarize yourself with the code. And what I will do is I will uh, do the same online, and you can ask me questions if there are any. So first is simple.
Hey, Unmesh, if you're sharing anything, I think it's not showing.
Oh man, okay. Oh, I was talking. Okay, man. Okay. Yeah, let me share the screen. Sorry. Okay. I'm so sorry. So one thing we want to do is, so did you at least see the slides that I was sharing or no?
Yeah. I think only when you went to the code.
Okay. Yeah, I forgot to share back there. Okay. Yeah. So in the code, I mean, what we just saw in the slides, right? If you can see this code in distributed transaction KV package or module, there are a bunch of exercises starting from how to handle begin transaction to how to write provisional intents, um, and then how to do transactional reads, and then commit and resolve. So what we'll do is we'll do these exercises one by one. You can do it on your own as well. I will do it online, sharing my screen. So for implementing all of or for finishing all these exercises, essentially they are all in this transactional storage replica, and the entry point is, if you can see, what all messages this transactional storage replica supports. So this first exercise that we looked at was implement this begin transaction method, and essentially we are creating a transaction record as we saw in the slides with a transaction ID and status as pending. And then we return the response back. Now, one thing to note is that while handling all the requests, we are following the hybrid clock rule that we talked about and implemented in the first two modules. So this is assumed that everything we are doing henceforward, essentially every data that we are storing and reading and all that, it all happens with hybrid timestamp as the version. So the first exercise was to just have this kind of a transaction record with us. You can continue doing on your own because I think it will give you, you can look at the code at your own pace and try to internalize it, understand it, and ask me questions. I will take a pause for some time.
Yeah, sure. One quick question is, when the transaction begins, is the client like explicitly aware of who is the coordinator, or is something?
Yes. So if you look at the transaction storage client,
okay.
There must be a begin. Yeah.
Okay,
so,
I think it's based on the transaction ID that
yeah, it's based on the transaction ID. So it's exactly the same. I mean, similar logic that you use for key routing.
Oh,
Um, yeah, based on transaction ID, you pick up one of the replicas as coordinator. So maybe we'll take like half an hour for, I mean, for you to just go through this code and try to implement these exercises. They are all, I mean, the exercises essentially are just completing some of the missing methods. All the other code is already in place, so it's more about going through the code and trying to understand it.
sure. Thanks.
Yeah. Cool. So let me just walk through the code and we'll discuss the basic implementation of snapshot isolation. And after that, I think we can close for today. The remaining anomalies that are out there, maybe we can take that more of a homework. But let's walk through the code because this is substantial amount of code that's implementing snapshot isolation as a whole. So let me just share my screen and we'll go through the exercises one by one. So the first thing I think is pretty straightforward, and as I said, everything that we are doing um, is in this transactional storage replica, and the entry point we always go to the type of messages this replica is supposed to handle. So we go to begin transactions request, and essentially we need to just put the record for transaction, and key things here are transaction ID. With the commit timestamp, we still don't have it. It will be set at the commit time, but we mark the status as pending. And other important thing is that um, we also track the transaction record for timeout. So if we do not receive commit in say certain amount of time, we automatically, this particular node can automatically mark this particular transaction as failed. So uh, so that it doesn't remain open um, for unknown amount of time. The next is where we handle the write requests within a transaction. And this goes to handle transaction write request. We will, so this is the last exercise we had to do, but we'll come to that at that point later. So before we write, we have to do certain check for handling read-write conflicts in um, isolation uh, to maintain snapshot isolation. But there are two important things happening here before uh, we write intent for a particular write. So we write this provisional record for this. If there is no existing intent for the given key, so if we find the latest intent for the given key, and if it's not there, and latest intent we find by similar technique we used earlier with the version value, and we give the maximum version number. But if there is no existing provisional write, that means there is no concurrent write operation happening, then we write into this intent store. So this was exercise 2, write into this intent store. And you can see that this provisional write is happening at whatever is the current timestamp at which the write request arrived on this node. But if there is an existing um, provisional write that's there, then we need to check if it's a pending transaction, there is a transaction that's still pending, or it is committed transaction. In that case, we have to do that write first and then continue with this transaction. Or if it's an aborted transaction, and in that case, we can just remove that provisional write. And for doing that, what we need to do is essentially send a message to the coordinator for uh, the transaction for which there is this provisional record, and then get the transaction status. And once we get the response back, from that response, we know if it is a pending transaction. If it's pending, we just fail the current write right away. But if it's not pending, then if it's either committed or abort, we handle that, and only then we write intent for this particular transaction. So this was exercise 2. Then we have to handle read requests, which are transactional read requests. Now they need to do two things. One is, if the read is part of the same transaction for which we have already written a provisional record, then we just return that value. But otherwise, we have to read from a different store, which is a committed data store at the read timestamp that we got when the transaction was started. So we again go back to the entry point, which is where we have registered all the requests. So this is transactional read request. And first we check if there is the transaction for which we are reading, if there is any provisional value that's already written, and if that's written, we return that value. And so this is read your own rights, as the comment says. If not, then we check if we need to resolve any ongoing transaction, and then we resolve that. And after resolution, we read from the committed transaction. So this is that. This is where we are handling the read requests. And the final is commit and resolve. And this is where our transaction coordinator needs to handle the um, the commit request, handle commit transaction request, and handle commit transaction request. What it does is, this was the fourth exercise. We check the transaction record for the transaction ID. In the commit request, we also get all the participants to which we have written the request, written any data to. So we mark this transaction record as committed, and we also assign a commit timestamp. This is a crucial. So current hybrid clock timestamp is assigned as a commit timestamp for this particular transaction, and then we send the requests to all the participants saying that this transaction is committed. But you can see that these are asynchronous requests. So we send and we don't really wait for the response, because any of the read requests that are going to those nodes are anyway going to resolve if these requests are missed by and then we send the commit response back. So this is what handling of the commit request was. And after these uh, implementations are done, you can see that this particular test should pass. Okay, I don't know why this is failing. Okay, yeah, I mean, it will fail. Okay, sorry, I was making the change. So one other thing, other change I was making was that these tests, if you see, they were running only on single node, but it doesn't need to be. So the logic is kind of independent of how many nodes we run um, this particular implementation with. You can add n number of nodes. Um, so you can actually right now try by changing the single node to 3 nodes, and the test should still pass. Only thing is that asserts where we are expecting a single node, those will fail. So if you debug and go there, obviously because the coordinator for and uh, the participants for each key were different, the transaction record will have different participants than, so it's storage node 2 right now, but it can differ. It really it really depends on the key. So what this needs to be is that we say client replica for whatever key we are. Okay, you want to try this out? Try out making changing this to 3 nodes instead of 1 node. I don't know where it's failing now. So as you can see, this has to be wherever the this particular key is routed to. So replica for key or replica ID for key. And then actually you have to say cluster dot get process replica. Yeah. So what you can do is you experiment with these kind of things. So you have these tests. You can try out n number of replicas with which you run this particular cluster, and then tweak the test and see what's happening. Now the last thing we need to see is how snapshot isolation validation. I mean, we have like 80% of or 90% of building blocks for implementing snapshot isolation. But the last check that we need to do is essentially the first committer wins check for snapshot isolation. And let's see how that's done. So if you can see the slides, there are we'll just walk through the basic flow of how snapshot isolation implementation is working currently in this particular implementation. So first important thing is when the client sends begin transaction request to the coordinator, um, there is a read timestamp that's assigned with coordinator's hybrid clock dot now. So whatever is the latest timestamp at coordinator at which this particular request is handled, it's assigned as the read timestamp. And then for any read requests or any requests that are sent um, from this client to any of the participants, read or write requests, this particular timestamp will be used as the read timestamp. And that's sent back to the client, obviously, from the coordinator. Now, when client sends the write request for some value, say x with value equal to 2, it checks if there is a already committed value. Um, so currently, what we are checking is if there is any active intent, and that means if there is any ongoing transaction. But now what we also need to test is if there is any already committed transaction after our transaction started. So after the read timestamp of our transaction, if there is any other transaction that's started, then we they need to know that. Now, what the diagram is showing is not that rule, but it's showing that any writes that happen, they write at the latest time at that particular participant. Right. So what's shown on the diagrams is the check that we need to do. Is there any already committed transaction? So it's not enough to test if there is any ongoing transaction, but if there is any already committed transaction after the read timestamp of the current transaction, and if we get that kind of a transaction, then what this means is that there is another transaction committed after the read snapshot of current transaction, and the snapshot isolation um, validation essentially says that we need to fail this particular transaction because there is another transaction that was committed after our read snapshot, and that's the check then we need to add and return an error. So if you see in the code, uh, let's go to the code. And we go to transaction storage replica, go to, so this is a crucial check that we are, so even before checking the intent, we check if there is any already committed value after the read timestamp. And if it exists, we need to fail this particular transaction. So this is the snapshot isolation implementation. And there are multiple aspects. I mean, this check is just the last thing that we did, but the crucial um, points were one, we used MVCC storage with hybrid timestamp that we have. We used separate commit store and intent store to separate out in-process transaction data and committed transaction data. And then we implemented something that is a two-phase commit, but a modified two-phase commit where each participant also resolves if there are any pending transactions that it finds. So this is a bare bone implementation of uh, snapshot isolation with transactional database with multi-version with hybrid timestamp. But any multi-version storage uh, or any transaction implementation, even without hybrid timestamp, you will see similar building blocks that are in place. So the intent was essentially just to uh, familiarize with the basic coding building blocks and patterns uh, that a typical transactional database uses, specifically with the usage of hybrid timestamps and hybrid clocks, which is typically done in modern databases like DB and causality. But what I will do is I will take a pause here, and other things I think you can take your time, because I think it will be good to spend more time with this code base and familiarize yourself with the concepts, and if get more questions and then see if this code base tries to answer those. And also possibly go through the actual Yugabyte or CockroachDB or MongoDB code bases to see what other things they do to make this more production robust implementation. But I will take a pause to see if there are any questions. And if not, I think we can close for today. And I'm happy to answer any questions if you have any. You can reach out to me on my email address, or over LinkedIn. But I'm open for any questions. Let's wait for a couple of minutes.
So Umesh, I have a very specific question, but I just want to understand from different types of database implementation like Yugabyte, causality, and DB, what
Yeah.
would be the differences? Any specific techniques each of these databases use, or overall whatever we discussed is what is
Yeah, so TieDB uses timestamp oracle, so it
correct?
won't be hybrid clock, but it will have the timestamp that the oracle gives it. So the implementation will look very similar. Um, Between Cockroach and Yugabyte, I mean, their implementation will look more like what the code base is. Exactly using hybrid clocks. Where they differ is essentially uh, details of, for example, we used separate RocksDB instances for intent and committed data storage, where CockroachDB uses same storage for both, just uses different prefixes for different kinds of data. Um, and that, I mean, that kind of implementation level variations are there, but at high level they are uh, almost the same.
Okay.
And
So
there is
now I think
other,
when we read these white papers, we'll be able to easily understand, I guess, the
yeah, I mean,
differences.
yeah, I'm not sure if easily, but at least have some mental model and reference code because there are so many nitty-gritties when these papers are written. I mean, they will probably just write a few lines about some of the key things, and it's very hard to relate to actual code when you try to relate. Yeah, so the idea was that you have some reference code, and that's not as complex as say production Yugabyte, because in this code, I mean, you can do whatever you want and uh, tweak it, change it, try out different things.
Yeah. Thank you very much for all this. I think it is very hard to get this type of information easily.
Yeah, I mean, this kind of information only lives in production code bases. There is no there is
Correct.
no book
Correct.
that talks
Correct.
about this. Yeah, yeah, and that's the reason I think even this workshop, I don't know. I mean, it's very hard to do it remotely. I thought uh, there are so many tricky things. And it also takes time to familiarize with the code base, right? I mean, even the code base that I have, I mean, it's not very. Uh, but yeah, I mean, I hope at least everyone got at least some head start
Yes, yes,
into.
definitely.
Yeah.
Yeah, yeah. Okay. Yeah, I mean, thank you very much because I mean, I know how hard it can be for this kind of a topic uh, and over Zoom. So yeah, I mean, thank you very much, and do send feedback if you have any. I will be making some more changes, I mean, based on this experience.
Yeah.
Yeah.
And now we discussed this part, the other part, like the query, how the queries are getting converted, and also the multimodal, how it is implemented. So those type of things where we can uh, get information. Now I think the storage part we discussed, transactions
Yeah,
we discussed,
storage we discussed. Yeah,
and
storage and transactions.
versioning.
Yeah, yeah. So query is another, I think, big thing. Um, but you can see that essentially it boils down to when it comes to storage, right? A key value is a good metaphor for any type of storage, and any query uh, that you write. Um, I mean, it obviously if it has a lot of joins and stuff like that, there are other complexities. Uh, but at least if on a single table, whatever query you write, it's very easy to translate that into what can be possibly happening on this key value store. For multimodal, as I said, you can map any. any type of storage to essentially key value. So I think that part is easier relatively.
So I have one more question. So now
Yeah.
we discuss these transactions across the multiple machines, right? So, but
Yes,
when we
yes.
are, let's say, storing the wide column into multiple key values, like each column is separately we are storing. So then,
Right.
let's say one key value we updated for one column, and by the time we are trying to, I mean, the system trying to update to another column, there could be some issues, right? So there also like some transaction at a multi-column storage also happens,
Yeah,
or that will be
but
much
see,
simpler transaction.
the conflicts you are checking are based on your primary key, essentially in this
Correct.
case.
Correct.
So whenever you store like different columns separately, your key prefix will always be your primary key, and that so your conflict detection logic will remain the same.
Correct. Okay.
Cool. Yeah, so we can close the call. Thank you very much
Thank
for
you.
attending.
Yeah,
Thank you.
thank you.